the session. And the first paper to be presented is Automatically Learning Formal Models, an industrial case from autonomous driving development. And the speaker is Ashfaq. So please go ahead, share your screen, unmute yourself, and good luck.
Thank you, Lucio. I'm just sharing my screen and I hope now everyone can see the presentation. So, welcome to this talk on automatically learning formal models. I am Ashfaq, and here I will present to you our work with Zensact, where we've been trying to learn models of their programs, of their self-driving car programs. Just a little background to the whole project. This is an industrial PhD project and in collaboration with Chalmers University and Zensact. Zensact is formerly known as Zenuity. It's a software company working with autonomous driving and advanced driver assistance systems. And they have offices both in China and Sweden. Their main focus is robustness and safety. And here we want to supplement robustness and safety with formal verification tools. And our project here looks at how we can use formal verification to further this goal. So the motivation, as uh, we are all here to talk about models, right? And we need models for formal verification. Uh, and from our experience, we know that learning or manually creating formal models is a really big obstacle, and it is error prone and quite intractable for large systems. Uh, let's say you do build a model, you do have some kind of a model for your system, but then the problem that happens is you have code that is changing, and as your code changes, you have to maintain both your code and uh, your model at the same time, and this becomes expensive as the development goes by. So we asked a question whether how can we make this manual construction more automatic or automate this system. So we want so our approach was, can we learn an automaton model from existing program code, and how do we do that? So we looked at two main algorithms, the L-star algorithm and the modular plant learner, MPL. The L-star is well known, coming from the 80s with Dana Angloin first presenting it. And modular plant learner is something we've been working on recently. Just to give you an overview of what these two algorithms are, the modular plant learner is a state-based learner in that it starts with the initial state and then tries to explore the system as it goes. So it starts from the initial state and sees what it can reach, what states can be reached from there. And once new states are found, it explores these states further, something like breadth first search, and it terminates when there is no more new states to be found. In the animation you see here, the states are represented by numbers, 0, 0, 0, 1, etc. These numbers actually hold significance here. They define unique states. Uh, and our modification, so I'm just giving you a very high level view of what the MPL is, but if you're interested, you can go ahead and read the reference papers. Uh, the L star is another approach, but here the focus is on learning the language of the system rather than finding the states. So the L star learns a global minimal language that describes our end system. Uh, it does so by looking for counterexamples. And counterexamples here are the key. So, for example, in this animation, you see it starts from an initial state and it asks if this initial state is a valid model. And if it is not a valid model, you need a counterexample to be given. And it incorporates this counterexample and then produces a new hypothesis. And this process continues till you can no longer find counterexamples. So the key here is generating uh, usable counterexamples. Again, I'm not getting into the details of the implementation, but feel free to reach out and discuss with me about them. Uh, so what we did here is we took the system, the lateral state manager as our case study, and we wanted to learn what the lateral state manager does and how can we automatically model this. So this comes from the decision making and planning submodule in the autonomous driving system, you have a high level planner here that requests a lane change, and the lateral state manager keeps track of where the car is to correctly give directions to the path planner on how to make the change. So, what do we need, or what do we have with the lateral state manager? Firstly, when the engineers designed the lateral state manager, they envisioned it to be a state machine. And this is seen in the slide here on the right. So, this is the rough description of how the lateral state manager should behave. Uh, and it is programmed in MATLAB. So, we need a way to interface with MATLAB. Another problem to learn the LSM is you have all these interactions here coming in from the high level planner, from the sense. So we need to somehow abstract them out so that the LSM is a unique module in itself. Uh, so that's two things we need to do. And the functionality. So we need a way to interface our learning algorithms with the LSM itself. So these are some things we did. And here is a high level overview of how it looks. So you have the LSM on the left side, and you have our learning algorithms, which we developed in Scala. Uh, to interface these two, we have a MATLAB Java interface that bridges between the two components, you can say. What this interface does is it has the ability to run a function in the LSM and report back its results to the learning algorithms. Uh, and also, we need to provide the learning algorithm with the initial state and the alphabet uh, of the system. So the learning happens once you have all this information and a model is given out. It's a finite state model we have. Uh, this finite state model can then be used for formal verification, formal synthesis, or even simulate it to see what you want to do. Uh, yeah. So going ahead. So what did we learn out of this? What were our outcomes? We saw that the L star did not terminate completely. And the MPL manages to learn a model that was valid, and we have good confidence to know that this model describes the behavior of the LSM. Uh, just yeah, to say something about the learned output of the MPL, we had uh, we had the learning done in 68 seconds with about 687 transitions and 37 states in total. The L star algorithm would be learning the minimal language. And as you will see now, the minimal language is what you see in the graph here, the minimized model. But still, the L star could not terminate because there were quite a large number of counterexamples to be found, and hence it ran out of memory basically. Uh, but anyhow, an important outcome was when we minimize the model we learned from the MPL, we get the output which is seen here, which very much resembles the original intended uh, state diagram the engineers had while developing their program. And that gives us a very high confidence on how well the system can be learned. Just as a side note here, you do not see the transition names because of proprietary reasons. And yeah, uh, in any case, so going ahead, we
Just a
had
second reminder that you have 2 minutes left.
yeah, uh, so some of the insights on what we learned was that there are practical challenges in applying this interface to a large scale learning setup. Basically, if we have a right now we had only MATLAB, but when we want to do this at a large scale for different systems, then you will need to have different interfaces for each and every subcomponent. So we need a way to scale it up and have a more general uh, interface. And then there is a possibility to use automatic abstractions because abstracting the code manually every time is tedious. And thirdly, there is a very big trade off between states and events. And this is shown in how we learn the model, as in the MPL could learn a small model because we had some kind of abstraction that allowed us to trade the number of states with the number of events. So as we scale up the events, we can reduce the number of states. And this requires domain level language, domain knowledge to actually cut it down during the abstraction phase. And then if we want to use this towards formal software development, we know that this method works, and it is really interesting for us to see how it can be taken forward. We are no longer interested in the semantics of the implementation language, other than the interface. And once we can abstract the interface itself, then we don't care what the underlying language the system is written in. And thirdly, we hope that this can be used in a continuous manner, something like regression tests done today to actually build up the formal model every day and test it against specification. This becomes really important when you have safety critical code that is changing at such a high pace. So we can actually use formal models and formal verification techniques on something like on the go. Uh, so just some points on future work. Uh, right now, the study was done on a very
robotic
specific.
arm, which is this diagram. And then in both
Uh, so this study was done on a very specific example, uh, and we don't know if there was some element
the
the
main idea
LSM
was
that actually of the LSM that actually made it good for this approach. We would like to see other subcomponents to learn to see how it behaves when we apply the same approach. Secondly, the models learned grew in size very quickly. So having more richer formalisms to describe these models would definitely be something to look at. For example, the EFA. And also, as I said previously, to have a continuous model in which we build and verify on the go as the software changes on a day-to-day basis would be something we are yeah, we would like to see that in action and take that forward. uh, so yeah, thank you for listening, and me and my co-author Yuvraj will be around in the conference, so if you have any questions you can just ping us. Yeah, thank you.
Thank you. Thank you so much for your talk and for being in time. Just I can remember to mute yourself